section 5.5 is on the factor and remainder theorems, and I would highly recommend that you watch these videos real carefully, take some good notes, pause the videos as you watch them, and make sure that you can work the problems out and not just listen to me work them out. This introduction, of course, is not necessarily going to be working through problems, but I wanted to start out with that warning. Things start to get a little more detailed in the following sections. So what the factor theorem and the remainder theorem is going to talk about is a process of division. And you've added polynomials, subtracted, and multiplied polynomials, and all of it, which are very easy. And division is like 2 sections long because it's really not that easy. So the first process when you divide is if you're dividing by a nice linear function like x plus 2 or x minus 5 or whatever, and the coefficient is equal to 1. Okay, so what you divide by must be linear, and the leading coefficient has to be 1 in order for this following process to work. Then the division process is actually quite simple. Off to the right, and you can certainly pause the video and jot these down, I'll be working through several examples later on, but these are the steps in dividing a polynomial function if and only if you're dividing by something that's linear with a leading coefficient of 1. So the first step is to set that denominator equal to 0. So that means I would take x plus 2 and set it equal to 0 and solve for x. And obviously x is going to be negative 2. So that's a piece of cake. Step 2 says using the result from step 1, so that negative 2, divide using synthetic division. Now you've done synthetic substitution. And good news is synthetic division is the same process, different result. Okay, so I'm going to actually go through step 2 really kind of a little bit quickly in my following videos. I'll remind you of all these steps. But you draw a half rectangular box and you take all the coefficients of your polynomial, including anything that's missing from the highest degree all the way to the constant. So for example, I have x to the 4th, which means I need x to the 3rd, x squared, x to the 1st, and x to the 0. So I have x to the 4th. I do not have an x cubed, so I'd have to toss in a 0. I do have an x squared, I have an x to the 1st, and I have a constant, so I have an x to the 0. So I'm going to take all those coefficients, so I have a 1, and I don't have a cubic. I have a 2x squared, a negative 1x, and a 5 as a constant. So again, this is my x to the 4th, x to the 3rd, not that you have to write these above it, x to the 1st, and x to the 0. That 0 is real important if you're missing something, and you'll see why in a second. Then you take the negative 2, which from step number 1, and you put it outside this little half rectangular box, and then you're just going to go through the synthetic substitution process, but now it's synthetic division, and I'll tell you why. But the process is the same, so you carry down the first number, you multiply, you add, you multiply, you add, you multiply, you add, you multiply, and you add. Now, with synthetic substitution, we only cared about that 31, and we knew that that would be our answer had we directly substituted negative 2 in for all the x's. However, what synthetic division is, and this is step number 3, your answer comes from all the resulting numbers, and the last number is your remainder. So because I took a 4th degree divided by a 1st degree, I know that my answer, my quotient, should be a 3rd degree. So that basically means all of these numbers down here are coefficients, and this is my x to the 3rd, x squared, x to the 1st, and then this is my remainder. Okay, now you can see, first of all, if you hadn't had the 0 here, these numbers would be off in your process, right? So that's very important. But again, I want you to understand that you're taking 4th degree divided by 1st degree. So if you just think about x to the 4th divided by x to the 1st, you know that that's x cubed, and that's why my resulting division process ends with x to the cube. So again, this is x cubed minus 2x squared plus 6x minus 13, and then your remainder you write as product of what you're dividing by. So remainder of 31 over x plus 2, because that's what I divided by. So a pretty cool process, but again, only works, unfortunately, if you're dividing by a nice linear function with a leading coefficient of 1. So if I were dividing by x squared, then we have a much larger process, and I will let you watch a video on that much larger process. But good news is really the focus of the next few sections is this synthetic division process. So if you have synthetic substitution down, then you probably have synthetic division down, but now we're putting a whole new meaning to the coefficients down here. So now you're going to be asked questions like, can you factor if you know a solution? So for example, if I told you, here's your polynomial function, and x equals negative 3, okay, is a solution, can you factor that? So if x equals negative 3 is a solution, then you also know that one of the factors is x plus 3, and I really want you to think about that, because x plus 3, if I set that equal to 0 and solve, I'm going to get negative 3, which is a solution. So understanding that connection between solution and factor, or 0, x-intercept, all the same thing, is very critical. So can you factor this? While looking at it, I have 4 terms, which is cubic, and maybe I could group. And it does group, but let's just pretend that you didn't notice that it grouped, or eventually you're going to be looking at ones that actually can't factor by grouping. Good news is, if I know this is a solution to this cubic function, then I can use synthetic division using that solution of negative 3. And again, I just talked about this process, so I have a cubic function, so I should have x to the third, x squared, x to the first, x to the 0, which I do. So I'm going to take all those coefficients and line them up here and do the process, which I think you're probably okay with at this point. And I get 0 at the end here, and I want to focus on this 0 at the end. Remember, this is your remainder. Does it make sense that if I know x equals negative 3 is a solution, so if I would divide by a solution, I would get a 0 remainder, and that absolutely should make sense, because if you know x equals negative 3 is a solution, that means it's an x-intercept, which means it's going to make y equal to 0, hence you should get a 0 remainder. Okay, so that's the first thing you should note. If you don't get 0, but you're told this is a solution, then you know you did something wrong in this process. Okay, the last thing then I want you to note is I was taking a cubic function and technically dividing by a linear function, right? So I should be down to a quadratic. So that means this is 4x squared. This is 0x. I'm not going to include that. And then this is minus 25. And can I factor? Well, I think you can factor that. I sure hope you can factor that. And that factors down to 2x plus 5 and 2x minus 5. And I know that if this is a solution, that this is a factor, so x plus 3 is included, and I certainly can factor that. So what's cool about this is you're going to, again, run into problems that don't factor by grouping. I'm going to give you a solution that will work, hence you know a factor, and you're going to use that to get down to a quadratic, and I promise you that if I want you to factor it, I'll make it factorable. And these 3, if you FOILed them out, you would get this cubic function back again. All right, last concept in this introduction, and can you find other zeros if you know a 0? Okay, so again, I've given you this cubic function, and then this is a 0 at the end here, so I know 6 is a 0. Remind yourself that a 0 is a solution, okay, or it's an x-intercept. All of those words mean the same thing. So if I know a 0, I know that x minus 6 would be a factor. Not that I need that, but just reminding you of the connection between a solution and a factor. So if I know one of the solutions, and I've got a cubic, again, anytime you're given a solution or a factor, you can use that synthetically to get down 1 degree. So if I'm at a cubic and I divide by this 6, I'm going to get down to a quadratic, and you know how to deal with quadratics. So I'm going to take my coefficients, 10x cubed, minus 51x squared, minus 63x, and plus 54, so I have all of them. I don't need a 0. And I'm dividing by my 0 of 6. Okay, and then this process should be familiar. Sorry, that's positive 9. And I get a 0 remainder, again, which is good because if this is a 0, then I shouldn't be getting any sort of remainder, so double check yourself there. And again, I went from a cubic dividing by something that's linear, because remind yourself that that 6 solution also has a factor of x minus 6, so I'm technically dividing by a nice linear. So that means I went from cubic to quadratic. So now with that, you could factor and solve. You could use the quadratic formula if it doesn't factor. So you would ask yourself, can I factor that? Possibly, or maybe not. Then you're going to use the quadratic formula if that's what you prefer, or you can complete the square if you like that process better. So all of that stuff from Chapter 4 coming back at you again. I do think that this one factors, and you can play around with that part of it because this shouldn't be new, but seeing if this is factorable. So if I did this, I'll just talk through it. So this would be 10x squared. My outer would be 15x, my inner would be negative 6, and 15 minus 6 is a positive 9, and negative 3 times 3 is 9. And if I set that equal to 0, and again, this should not be anything new, set each of those equal to 0 and solve them, then I know that my solutions are going to be x equals 3/5 and x equals negative 3/2. And there are my other two solutions in addition to the 6 that was given.